Assalamu alaikum. In this video, let's look about radioactivity. This is the last part in our matter and radiation unit. So, radiations. Radiations. These radiations contain alpha, beta, gamma. They are emitted spontaneously when an unstable nucleus disintegrates to acquire more stable state is known as radioactivity. What does that mean is we have a nucleus, let's say that is X. Now this is unstable. This becomes stable by releasing some radiations, alpha, beta or gamma radiations. During that, a new element or a new nucleus is formed, and we call that new nucleus as the daughter nucleus, where before the radiation or that unstable nucleus, we call it as the parent nucleus. These alpha, beta, gamma rays, they are also known as the Becquerel rays. And Madame Marie Curie discovered a lot of radioactive sources such as polonium, radium, uranium, and so on. Now, let us look at what are these alpha, beta, and gamma rays. So let's go through each of them separately. First, let us look at what is this alpha particle. Alpha particle, it contains two protons and two neutrons. That means the alpha particle has two protons. That means its charge is 2, and it has two more neutrons. So its mass number becomes the sum of number of neutrons plus the number of protons. Therefore, it becomes 4. And this is similar to the nucleus of helium. Helium has two protons and it also has two neutrons. Therefore, uh, electrons removed. When you remove the electrons, this is what we get. So, alpha particle is also identified as the helium nucleus. So, alpha particle is similar to the helium nucleus. Now, let's say when a nucleus undergoes alpha decay, during alpha decay, it will lose 4 nucleons. When we say nucleons, it is protons and neutrons together. Now, let's say we have a nucleus whose atomic number is Z and the mass number is A. During alpha decay, it will release 2 protons and 4 nucleons, or 2 protons, 2 neutrons. That means the daughter nucleus, it will have less protons. It will have 2 less protons and its mass number will reduce by 4. Let's look at an example. Here we have radium 226. It undergoes alpha decay. When it undergoes alpha decay, it forms radon, as I remember. So, if it releases a alpha particle, its atomic number becomes 86 and its mass number reduces by 4, therefore it becomes 222. One more example, uranium 238. So this uranium 238 undergoes alpha decay. So its atomic number reduces by 2 and mass number reduces by 4 to produce thorium. Now, if you look, we started with some element but ended with another element. The formation of elements after radioactive decay of some element is called transmutation. So one element producing another element, we call it as transmutation, just like here. Here it has undergone transmutation. Next, let us look at what is this beta decay. Beta decay, these are very fast moving electrons or positrons. We will be studying about positrons finally in this part. Positrons is the opposite of an or the antiparticle of an electron. So that is the antiparticle of an electron. So its charge is going to be positive, just like an electron. Now let's say the number of neutrons is greater than the number of protons. So the ratio N over P is going to be greater than 1, right? Now there is excess neutrons. And when there is excess neutrons, these nucleus try to convert them into proton. So later you will study that the nucleus is formed by quarks. So the neutrons and protons, they are formed by quarks. So proton can change into neutron or neutron can become proton by releasing these quarks. Not the quarks, what quarks are made up of, releasing those particles, they may become proton to neutron or a neutron to proton. Anything could occur. Now let's see how a neutron can become a proton. Neutron has no charge, it's neutral. So the neutron, it is neutral. It doesn't have any charge. But then we have a proton. A proton has charge. And let's look at their atomic number. Atomic number remains the same. So how is this possible? It is by releasing a electron. The electron, it has a negative 1 charge and no mass. Now when you look both the sides, the charges are balanced, right? The charges are balanced as well as the atomic mass is balanced. Now you have to understand that this electron over here, it is not released from the atomic orbits. It is not released from there. It is released from the nucleus. So it is released from the nucleus. And then we have one more particle. We call this as the neutrino. And we have a bar above this that means antineutrino. This antineutrino was not identified initially, but they when they conducted experiment, this experiment always would deviate the law of momentum, conservation of momentum, and also it would deviate the conservation of energy. Like uh, so then they came up with an idea that there is one more particle that will make these two laws, that will make this reaction to obey these two laws. And later that particle was found and it was named as antineutrino. Then we have uh, so this is beta minus particle. So when nucleus undergoes beta minus decay, so remember, beta decay could be electron decay or it could be positron decay. So if it is electron decay, we call it as beta minus decay, and if it is positron decay, we call it as beta plus decay. So here we have a nucleus. This nucleus undergoes beta decay. During beta decay, the atomic number doesn't change. It remains the same. But the charge will increase by 1. During this, a electron or a beta minus particle is emitted to conserve the for the conservation of momentum and the conservation of energy. We have one more particle, the antineutrino. So it's like this. So that's the symbol for antineutrino. Now let's look at beta plus decay. So in a beta plus decay, we have a proton that will get converted into a neutron. So during this, a positron is emitted. Now let's look. The atomic number won't change, but we have a positive 1 charge. By releasing this positive charge, it becomes neutral. And during this, again for the conservation of momentum and the conservation of energy, neutrino particles are released. So for the principle of conservation of momentum and the conservation of energy, emission of neutrino or antineutrino is necessary. So remember, when we have beta minus decay, it's the antineutrino. When we have beta plus decay, it's the neutrino. And finally, so this here also, what is happening? A nucleus forms another nucleus, another element, a new element. Therefore, during a beta plus or a beta minus decay, transmutation occurs. Transmutation occurs. And finally, let's look at gamma decay. During gamma decay, nucleus which possess greater internal energy emit gamma rays to acquire more stable state. So let's say we have an element X, it's excited and it releases or it emits gamma radiations and it becomes stable. So it is losing energy only. So here there is only the emission of energy. The atomic number doesn't change, therefore no transmutation. When we have alpha decay or beta decay, there is transmutation, but during gamma decay, no transmutation. Now let's compare these particles, alpha, beta and gamma. So alpha is the helium nucleus, where beta could be fast moving electron or positron, and gamma rays, it is just electromagnetic wave. The symbol for alpha, we use alpha 24 or helium 24. Beta, it could be beta minus if it was an electron emission, and beta plus if it was a positron emission. And gamma rays, it's gamma 00. The speed. The speed of alpha rays are very less compared to the speed of light. It is up to 5% of the speed of light. And then we have the beta emission. Here it says it can reach up to 98% of C. The idea of this is it doesn't have a specified speed. Instead, we could have, when we conduct the experiment, or when there is a beta decay, it releases this electron particle. And this electron particle, it doesn't always have the same speed. At times it might have a greater speed, or it could have a less speed. It depends. Even if we do the same experiment again and again, it depends. So the maximum it could reach is only up to 98% of C. So it is not moving at the speed of light, but it is moving less than the speed of light. So again, this is the reason they had to introduce a neutrino particle. That is because when they conduct an experiment, or when they did that beta emission experiment, let's say we have a reaction. During that reaction, only electron emissions are observed. Only the emission of electron is observed. So if we conduct the experiment again and again, we must be having, so we know this reaction, it is going to have a certain amount of energy released, right, during that experiment or during that emission. So if that energy was given only to electron emission, then it should possess the same amount of kinetic energy in each and every experiment. But it is varying a lot. At times it is high, at times it is less. Then there should be some other particle which will take that energy, right? That is why they had to introduce the electron neutrino, or the neutrino particle. In case of beta minus emission, it is the anti-neutrino. And let's look at the mass. The mass is 6.4 into 10 to the negative 27 kilogram. So we know what is the mass of proton, and it is 4 times of that. And here this is the mass of an electron. Gamma rays, they don't have a mass. Let's look at the charge. The charge is going to be plus 2 times of an electron. This is the charge of an electron. Gamma rays don't have charge. Reflection by electric field, yes, because it's a charge. This is also yes, but gamma rays, no. Do they affect photographic film, and do they show fluorescence? Yes, yes, yes. All of them do. And how about the penetrating power? For alpha particles, it is very low. The reason, alpha particles are huge in size, therefore they are not able to pass through atoms. Therefore, the penetration power is low. If we take the penetration of power of alpha as 1, Then we have the beta minus decay, which has a intermediate penetrating power. It could be 100 times of alpha, because we know electrons are small, they could go through those materials. And then we have gamma rays. Those gamma rays are radiation which can pass through. They have high energy. So when compared relatively, it's 10 to the power 4 times that of alpha. Then we have the ionization power. Alpha, it has +2 charge. So it could ionize materials very quickly. So its ionizing power is very high. If we say the ionizing power of alpha to be 10 to the power 4, then we have the beta emission, which is high, or 10 to the power 2, and gamma, it's low, it has very less ionization power. Now let's look how we can identify these particles alpha, beta and gamma in electric and magnetic field. In case of gamma rays, they are not deflected by electric field and they are not deflected by magnetic field. Therefore, those radiation will just travel straight to the screen and make a fluorescence. Similarly, it is for magnetic field. Let's look how electric field affects beta and alpha and beta particles. We know that alpha is positively charged. If we set up an electric field, here it's set up towards your left, so the positive charge will be deflected towards left and the negative charge will be deflected towards right. And we know that F is equal to EQ, electric field strength is the same. Then we have Q. Q is the charge, and the alpha particle has twice the charge of beta particle. Therefore, the force on the alpha particle is 2 times of F, if F is the force on the beta particle. So the alpha particle, as it is having more force on it, its deflection will be greater. Alpha particle deflects a lot, and beta particle, it deflects but it's comparatively lower than that of alpha. In magnetic field, here we have a magnetic field into the screen. It's shown here how the forces are going to act. Using Fleming's left hand rule, we can find this is the direction of current. Because it's positive charge, then we have force towards our left. Because this is negatively charged, current is opposite, so you get force towards your right. We know that F is equal to BQV. Q alpha is greater than Q beta, but so this only differs if this is 1, this is twice of that. But let's look at the speed. Alpha has very low speed compared to beta. This is only 5% of C, but this could go up to 98% of C. Therefore, than charge, speed is significant. The velocity of the particle is significant. From that, we can conclude force on force F1, that's the force on alpha, is less than the force on beta. Therefore, F1 is less than F2. Beta particle deflects a lot and alpha particle deflects less. So in magnetic field, alpha deflect less, beta deflect more. And in electric field, it is the opposite. Alpha deflect more, beta deflect less. Next, let us look at the law of radioactive disintegration. Disintegration means when unstable nucleus turns into a stable nucleus. So let's look at the law. The rate of decay of a radioactive sample at any instant, very important, is directly proportional to the number of atoms present at that instant. So according to that law, rate of decay proportional to number of atoms. dN over dt proportional to n, we have a negative in front to show it decreases. So the equation is minus dN over dt is equal lambda times n. From this, we can get this equation, but in our syllabus, it's not necessary. This equation is also not in our syllabus, but let's look what that equation tells. N is equal N naught E minus lambda T. N naught is the initial amount, that's the initial, and here T is the time. T is the time. With time, we can find after a certain period of time what will be the number of atoms remaining. Next, let's look at what is half-life. Half-life is the time taken for the number of active nuclei to drop to half of its original value. It is known as the half-life. We have n number of molecules. N number of nucleus or atoms. So this n number of atoms, it turns to n by 2 number. For that, let's say it took a time of t half. T is the time to show its half-life. Let's say t half. Then what will be the time taken by the same atom to turn to a number of n by 4? So again, it's another half-life. Look what half-life says. Here, look at the law. It says the rate is proportional to the number of atoms present at that instant. So initially we had n atoms. So to become n by 2, it took t half time. Now there is only n by 2 atoms. To become half of it means to become n by 4. It will take another t half time. So the time is 2t half. What will be the time for the concentration to become n by 8, or the number of atoms to become n by 8? It will take another half-life. So t 3t half. So from n to n by 8, let's say half-life of a certain element is 2 years. We want to find the time taken for the number of atoms to become n over 64. How much of time it is going to take? For that, we have to do this way. N from n to n by 2, it's going to take 2 years. N to n by 4, another 2 years. N to n by 8, another 2 years. N to 16, then n by 32, and then we have n by 64. So 2, 4, 6, 8, 10, 12. It is going to take 12 years to go from n to n by 64. So hope you got the idea. So every time you don't need to write this way to find how much time it will take. Look, we have 1, 2, 3, 4, 5, 6. n to the power 64. 2 to the power. So now let's say from n to n by 64, right? We can write this one in terms of 2 to the power. That is n over 2 to the power 8. So it will have the time taken is 8 times the half-life. 8 times 2 to the power of 8. Give me a minute. It's 2 to the power 6, right? 2 to the power 5 is 32. Yeah, it's 2 to the power 6. So it will take 6 half-lives. So using that, we can easily find. Now let's say the concentration or the number of atoms to go from n to n by 32, and the T half-life is given as 1.5 years. Then we have to write this in terms of 2 to the power. So that is 2 to the power 5. So the time is equal to 5 times half-life. That's 5, 2.5, 7.5 years. Let's get an equation for half-life. In your MCQs, you're going to do this way. Okay, in MCQs, you're going to follow this method. In some questions, essay related question, you might need this idea. So n is equal to n naught e minus lambda t. We have already looked for this equation. Half-life means that n should become n naught by 2 in half the initial amount. So if I substitute n with n by 2, n and n cancels, then we have half is equal e minus lambda t by 2. So take 2 to the other side, and because we have negative, let's take it to the numerator. It becomes positive. Then we have e lambda t half is equal to 2. Introduce ln. Ln is a natural logarithm. It will follow all the properties or all the laws of logarithm. Nothing new. You can just take this in front. Lambda t to the power half is equal ln e is equal to ln2. What is this ln? That is log e, base e. That is what we write as ln. So log e, that means ln e is equal to 1. Because it is equal to 1, then lambda t half is equal ln2. So t half is equal ln2 over lambda. ln2, we can substitute the value. It is almost equal to 0.693. For the rate of decay of the radioactive sample, we also have another name called as activity. So minus dn over dt, we can replace that with activity, that is capital A. So we can show that activity also has the same equation. Activity depends on time, and luck, it depends on the initial amount. So lambda, what is this lambda? Can you remember? We introduced activity is proportional to the number present, right? And then to make into an equation, we introduce A is equal lambda times n naught over here. So this lambda, it depends only on the nature of source. It does not depend on the pressure, temperature, or concentration. It does not depend on any of them. Because we know that activity is proportional to the number of atoms only. Okay, it is proportional to the number of atoms only. But still, if we have the same number of atoms of certain element X and certain element Y, we have different activities. And that is changed, or that is represented by this lambda in this equation. So lambda, it's the nature of that element, right? And this lambda, it won't depend on what's the pressure, temperature, or the concentration. If it depends on pressure, temperature, and concentration, then it is obvious that we cannot have the same half-life to go from n to n by 2 or n by 2 to n by 4. It won't have the same half-life or the same time if they depended on temperature, pressure, or concentration, because we could have changed them, right? But here we are not able to change them. That proves that lambda does not depend on them. Then what is the unit we use to show activity? That is becquerels. So 1 becquerel, that means 1 disintegration per second. That means one element or one atom undergoes a nuclear reaction. So yeah, it's releasing alpha rays. It's releasing radiation, only one radiation per second. That is 1 becquerel. And then we have another unit, curie. So 1 curie is equal to 3.7 into 10 to the power 10 becquerels, or 37 gigabecquerel. Although we have two units, becquerel and curie, the SI unit is becquerel.